The first half of this chapter, which some of it I'm going to sort of maybe jump over part of it today and come back to it next week, is theoretical and makes connections to the previous chapters. A lot of it is much more practical and hands-on, all right? And I kind of want to focus on that side of things today if I can. So we're going to talk in this new chapter about capacitance. Capacitance, a new term, a new idea, and hopefully I can make some connections to what we've already talked about. So, first of all, this is an actual physical device, something we can touch, something we can use, something that can harm us if we're not careful, all right? A capacitor is a device that has capacitance, we'll say, and it's something that can store electrical charge. It stores it in such a way that I can use it at a later time. It can store it for a very long time, and it's also quite temporary. When I charge it in a way and put charge on there and then use the charge, it's sort of gone in a flash, and I have to go back and charge it up again, all right? So it's a simple mechanism that really doesn't have any source of anything in and of itself. It's not really special, and as I describe it, you'll see how not special it is. But it allows us to store charge temporarily and get it back later and get it to do some work for us. So, the basic idea of this capacitor is simply putting two conductors, two pieces of conducting material in some shape or other, very close to each other, and then separating those two conductors by an insulator. We take two conductors, put them really close. In fact, as we'll see, the closer the better. But we don't let them touch. We keep them separated by an insulator. So for most of this chapter, we're just going to let that insulator be air. It's good enough for our purposes. It helps us understand what's going to happen. As we get to the end of the chapter, we'll change the insulator, which we'll see allows us in ways to make the capacitor operate better. Okay? So two conductors positioned very close to each other, separated by an insulator. And the most common case of this is drawn below. And weirdly enough, we've seen this shape a few times before. We haven't talked about what it is. We've talked about this theoretical thing that's like, all these positive charges and all these negative charges that creates an electric field in between that's constant and points directly from one to the other. What we didn't say is we were talking about this device known as a capacitor and learning a lot about the theory of what's happening in between. So if you want to, think about like we had this idea of like, there's this electric field happening. And now we're backing up and actually seeing what's creating that special electric field that we've been studying. We're looking at the device that's doing that. So you'll notice, there you go. This is two flat planes that are conductors. They're positioned close to each other, and they're separated by just air. Okay? This configuration is what we call the parallel plate capacitor. And it's the one that we're going to use most often to learn from. We'll look at some other configurations just so that you're aware of them. But this is the one we're sort of always going to go back to. Parallel plate capacitor, I think, that's pretty obvious. It's two plates. They're parallel to each other. End of story. Okay? You will notice a couple of different things. First of all, they are separated by a distance d. We'll come back to that on the next slide. And we'll say that each one of those plates, the conductors, has a surface area that can contain charge that's equal to A, and both of them should be the same. You'll notice right next to that sometimes it's really convenient if I want a big parallel plate capacitor. In other words, I want the area to be maximized. That can get a little unwieldy because it's like, now the area spreads out. I can take this configuration and roll it up like a little snack in a way, all right? Reminds me of what is that called? A fruit roll-up? I wasn't going there. I was thinking chocolate with like a white cream inside. It's still not a fruit roll-up. We don't want fruit. Fruit bad. Try again. What else you got? A Tootsie Roll and eclair? It's not really an eclair. A sponge cake like separated by layers of cream. It's not a Twinkie either. Do you people not know your snacks? Do we need to take a little visit down to like Walgreens or something and just look at that aisle? Swiss roll. That's what we're looking for. Yeah. What is that? That's not a banana. I really feel like we need to take a step back and just have a lecture on snacks, right? Because that was just sad. Yeah? Okay, should I prepare that for Monday when we're not here? Yeah. No. So, take this, make it really big, huge, large plates, and then we can just sort of roll that up to get a large area into a smaller space. So sometimes that might be referred to as a cylindrical capacitor, but we're going to see there are other types of cylindrical capacitors. It might be best to describe this as, like it says, a rolled up parallel plate capacitor to avoid confusion. When we do that, an extra step has to be taken, and you will notice they have added it in there and drawn it out. We've got one plate, we've got another plate. Well, I can't just roll it up so that these two plates touch each other, otherwise I've got conductors touching. I have to put another level of insulator in there to make sure that the backside of the parallel plates don't touch, okay? Ooh, that's just kind of creepy the more we go in. Looks a little tasty though, doesn't it? Okay, I'm going to zoom back out. I'm done with that, all right? We're going to use a couple of different symbols to represent the capacitor. And please don't think these symbols are complicated, because they're not. To represent the capacitor, we're literally going to draw a tiny little parallel plate capacitor. In other words, in diagrams of electrical circuits, we'll draw something that just looks like this with two little wires coming out the side, and we'll say, that represents a capacitor no matter what type it is, just because sort of the parallel plate capacitor is the iconic idea of a capacitor. Sometimes, and I typically don't use this, and I'm not sure why it's used, you might see one of these lines curved. So if you happen to look at a diagram and see that, that means the same thing. I don't like that one as much, because then I have to draw a curved line, and I don't know. It all of a sudden feels like I'm drawing, and that's no good. Yes? The distance D on this one is still like whatever this is. Ooh. That's it's whatever the width of the insulator is. Yep. Okay. Anyone else about anything here that's bothering you? We're doing okay? So, a word of warning before we go farther. Let's zoom in down here. Ooh. These are physical, actual capacitors that you might run into out there in the wild. You never know. You might just be wandering across campus, and all of a sudden, I'm sorry. Wow. You really were focused, weren't you? I'm scared now, too. So you might run across a wild capacitor. You never know. And you might be like, hey, look at that. I saw that thing like in class. I think I'll pick it up. Be careful. And also, please don't be scared if I yell. This reminds me. Quick story. Yeah. The other day, my wife was leaving for work at like 5:30 in the morning or something. Being a doctor is terrible. Like, why do you people want to do this? Like, yeah, what kind of hours is that? So, like, I was, like, she opens the door kind of behind her and waves goodbye, and I forget what it was. I think I was just shocked that it was just so dark still. And I just kind of stared past her, right, and was just like, like this. Of course, it never crossed my mind. She interpreted it completely the other way around, as if I saw something behind her, and it scared me. So immediately she's like, what is it? Like, I don't know if she thought there was a bear, a burglar, someone with a gun, like anything could have been out there in the darkness. But, I felt bad. Her heart rate was up. Like, I had to check her blood pressure then. No, like I know how to do that. Like, I'm one of those doctors that's not useful, really in any way, Like, she's the useful kind of doctor. So anyway, your screaming made me think of that. Are you okay now? You settled down? Yeah, you don't need caffeine for the rest of the day, do you? So anyway, taking a look at these, if we were to take any of these apart and look inside, we will find conductors that are really close together, separated by an insulator. In fact, if you look at just like one of these, you can kind of imagine, a couple of parallel plates inside there. If you look at something like this, you can imagine, maybe they took some parallel plates and rolled them up, okay? The thing about capacitors is that it's possible for them to hold charge indefinitely. And they can actually hold a lot of charge. A significant capacitor could actually kill you dead, okay? Things are dangerous. Yeah, you're like, kill you dead as opposed to what else? Like, I don't know. That sounded better for emphasis, I thought. So, I don't know. If you're someone that likes to play around with old electronics, there's always a few that are hiding around. You're just like, I like to take things apart and just see what happens. Old televisions, the kind that were almost before you all were born, that were, this thick, right? And weighed a ton because they have like a huge thing of glass on the front and are terrible. They're known to have relatively powerful capacitors inside. So I could imagine someone like goes to a junkyard and it's just like, look at this. Look at this dinosaur of a television. It doesn't work anymore. I think I'm going to beat it apart and see what's on the inside. So you decide to start doing that with, I don't know what this is exactly, and you rip it apart and you look inside and you're like, circuits! I learned about circuits in class. And then you're like, ooh, look at that big thing. That looks like a capacitor. And then you reach in and then you die. And I feel bad because I introduced you to capacitors, right? And then you're all curious and then you die. So just be careful. They can store charge. Like that TV might have been there for 20 years and there could just be sort of this snake in hiding, waiting to bite, all right? So if you stumble on a capacitor in the wild, don't just pick it up. Just be a little careful, all right? We will learn later on how to maybe safely handle that and get rid of the charge so that it goes somewhere besides through your heart, which is where you don't want it to go, all right? So, can we move on? Are you scared enough now? I don't know if you're going to stumble on a wild capacitor on the way home today. Probably not. Let's move on, all right? So, how does this whole thing happen? Charging the capacitor. How do we get this weird little structure to do anything for us? In fact, you might even ask the question, why would two just pieces of metal positioned close to each other do anything at all? In a way, it almost seems miraculous that we can create something so simple that, as we'll see later, can do so much. Okay, it's a really, really simple physical device. So how do we charge this thing? We charge it by connecting it to something that can provide a voltage. Think of this as a source of potential difference, if you want to go back to last chapter. And another device that we don't know a whole lot about yet, called a battery, which we all use all the time, is something that provides a source of potential difference. We're not going to talk too much now about how it does that. I think next chapter, or it could be 2 chapters from now, we go a little bit further into the battery. It's not really the focus of this class. Let's just say it's a magical chemical box. How's that work for you? Okay? It's a magical chemical box that creates a potential difference. In fact, one side of it will be at a high potential, and the other side of it will be at a low potential. What do I mean by sides of a battery? Well, just take a look at this one. Isn't that a lovely battery? Looks like a car battery, all right? It's a big box. There's chemistry stuff going on inside, all right? And when I say side, I mean there will typically be 2 conductors somewhere that you can make a connection to. One of those conductors will literally be a physical spot that is at high potential, and the other one will be at low potential. So you can imagine if I connect those 2 things together, any charges that happen to be at the high potential have high potential energy, and they would very much like to get to the low potential energy, okay? Making a connection allows charges from one side to get to the other side. If I don't make that connection, well, they can't go there, all right? So what we do is make this connection with a wire up to one side of our parallel plate capacitor. So this is a wire, it's going to be a conductor, and we'll make another connection with another wire over to the other side. Now let's think a little bit about what we learned last chapter. Conductors. What do we know about conductors and potential? What's that? There's no change in potential anywhere on a conductor. We said that a conductor is an equipotential surface. The potential is exactly the same anywhere on a conductor. So that means that once I've made this connection, you can imagine that all of this, all of this, all of that even, is like one conductor now. It's all connected without a break anywhere in there. All of that is an equipotential surface. And let's just go ahead and put a little plus on that to differentiate. We'll say it's the positive equipotential surface. It's the higher potential one. And you can already guess what's happening on the other side. Well, if that's an equipotential surface, well, I also made this connection. All of that is what we would call a negative equipotential surface. Every point on that common conductor on the left is at high potential, and every point at that conductor on the right is at the same lower potential. Are we still doing okay? It doesn't really answer yet how anything charges, but I'll tell you that next. Yes? Why is there no change in potential? I'm going to just refer you back to the last chapter, okay? As opposed to trying to go through one of those slides again. No change in potential on a conductor. So what happens when I make this connection? At this point, something is happening upstairs. I don't know what. I think someone stumbled into a stray capacitor. I don't know what's happening up there. What happens when I make this connection? We're going to have to sort of zoom out and slow down time a little bit because this configuration happens really fast. When I make this connection with these conductors, it sets up this equipotential surface really, really fast, but we can still sort of zoom in on that little tiny bit of time and take a look at what happens, okay? And what happens is this. You might imagine that, well, down here at this positive side of the battery, like kind of stored over here on the left side, is a bunch of positive charge. And please don't take this too literally. It'll help us understand what's happening, though, and it's roughly true, okay? On the other side of that, well, you might think of this as a lot of negative charge. So in other words, we have a net positive on one side and a net negative on the other. This is maintained. This charge separation is because work is being done by the chemical reaction. It's the thing that's taking something that might have been neutral before and making one of it net positive, one side net positive, and one side net negative, okay? So the chemistry is what's doing that, and it's maintaining that separation such that if all of a sudden one of these positives decides to go that way, it's like this chemical reaction. Let's just do this and call it like magic. See? You like that? Does a little bit of work to just sort of replace that charge right away, okay? Until the chemistry's all done and it basically wears out. At some point that will, of course, happen. So what happens when I make this connection? You might imagine that all those positive charges in there, they're all bunched up, they're close to each other. They don't really want to be, right? It's kind of like when this classroom is completely full, right? It's like, yeah, I'd really like to get out of here. It's just too many students, too many people. Like, let's all get away from each other. There's a repulsive force. And if I give them a place to go, they're going to go, all right? So as soon as I make this connection, it's almost like these positive charges down here at the bottom can sense that someone opened up another room, all right? This huge, relatively conducting area up here can store charge. There's a place there for the positive charges to go. So as soon as that happens, it's almost like this room is completely packed, and like, LeConte 4 down there all of a sudden is completely empty. And then someone opens these doors and says, if you want to go ahead. And then people in here start just rushing down the hallway and begin filling up the other classroom because it was just too much, okay? Too many people, too much repulsion. Well, that's going to happen for a little while. You might imagine that now, like, okay, positive charges as drawn here begin to start to build up. And then those are repelling each other, right? Like the first one goes down and it's like, LeConte 4 all to myself. This is fantastic. And then the second person comes in and then they kind of stare at each other. Like, I kind of wanted this room to myself. Why'd you come in here? And there's a little bit of repulsion. They're like, fine, we'll sit on opposite side of the room. We'll be good. Then the third one comes, and then the fourth one, then the fifth one. And you can imagine that on that first plate there's some repulsion that happens, and then eventually it balances out, right? The repulsive force from them on the battery sort of balances with the repulsive force of all the charges that have now taken up the space on one plate of the capacitor, okay? And when that kind of finalizes and it's equal amounts of repulsion both ways, everything stops and stabilizes, okay? That's how things build up on the positive side of the plate. You can also imagine that, as we'll see later, that doesn't really happen like in a constant fashion. It's like it starts out really fast, and then as there's more and more buildup on the plate, it sort of dies out and eventually stops. It's not sort of like an immediate, like 6 of you go over there and then it stops. It's like a rush, and then it sort of dwindles out. In another chapter, we'll mathematically look at that process, all right? So now I've got positive charges that are on the left plate. While that was happening, well, the other plate started out completely neutral, and it is really close. It's right next door. Maybe it's LeConte 3, okay? It's the other classroom that's there, all right? And everything was perfectly happy in there before. But now, like, noise is starting to build up in LeConte 4, right? And the people in 3 are like, I'm kind of getting tired of this noise. And they start to leave. In other words, you can imagine that positive charges that are in the plate right next door start to be repelled because of the buildup of charge on the left plate. Again, remember, these are conductors that are really close together. Whatever repulsive forces are there, like it's close enough that they can reach across that barrier and affect the charges that are in the right plate, okay? So during this whole process, I lose my iPad, which is apparently over here. Positive charges that were here are deciding to, let's get out of here. Off they go. And of course, if positives leave, well, now I've got a net negative on that side, okay? Once this is all done, once all the repulsive forces have sort of balanced out, which is likely microseconds, maybe milliseconds. Depending on the capacitor, maybe we can stretch it even longer. But think really fast. It's like I make the connection with the wires to the battery, charges go bloop, and then you're kind of done. Okay? And then it's in a steady state. Well, then all I need to do is sort of go here to the bottom and take these wires off, or maybe cut them here in some ways, and now I've got a capacitor that is kind of like a mini version of the battery, right? Because it has positive charge and negative charge. They're separated. There's no magic chemistry that's in there, so I could connect them to something else, and the positive charges will go whee because they're repelled, and then everything will kind of balance out once again. But now this capacitor is just 2 pieces of conducting material again. I have to go back to something that can charge it back up. It's kind of a one time, and it's done until I recharge it, okay? Tell me if this has occurred in your lifetime. I need new examples, I think. Disposable cameras. Did you use those at any point? Can you even still buy a disposable camera? Does anybody bother? It kind of, it's like disposable cameras were a thing, and then all of a sudden smartphones, yeah, right? Disposable cameras, a little bit of film that's in there, or maybe a digital card that can store a few photos and done. Typically, it has a button on there to charge up a flash, right? And you push the button, and you hear a little noise. Can you do it? Definitely not that. It's kind of like a little high-pitched. It kind of goes up and then fades away, and it's kind of done. Kind of sounds like charging, right? It's like starts low and goes, and then it's done. And you're like, I'm ready to take a picture, and it'll flash. And then when it's done, it's like, oh, I got to take another picture. I need my flash again. You got to hold down the little button, and it goes. That's a capacitor charging, and then it discharges through the flash and creates light instantaneously, and it's done. Okay. I don't know what else to say about that. Does anybody have any questions about this process? Yes.
When the positive charges leave from the battery,
It's a good question. You might imagine like they go there and sort of enter the magic chemistry once again, which allows them to separate from the negatives. This is sort of an approximate version of what's actually happening. keep in mind, there are no positives going anywhere. It's really electrons, but maybe it makes more sense from the standpoint of electrons. Yes? I don't know if those have capacitors. You connect it to another battery unless it's some kind of separate apparatus. I don't know enough about it. I haven't ever jump-started a car. I don't think. What's that? I am missing out on possible death. Defibrillator. I'm sure there's one right here somewhere, probably just down the hall, those portable ones. That's got a big capacitor in there, right? You like push the buttons to charge the thing and then, you know, all that happens. No, it's not really like that. Notice on the right. This is just a simplified drawing, a circuit diagram. Our first circuit diagram that shows exactly what's in part A there, just without all the nice little artwork, okay? So you can see that the capacitor, instead of actually drawing the plates with the charges, we've represented that with just, well, our little symbol for a parallel plate capacitor. And the battery has a symbol of its own, which you can see is similar to the capacitor symbol, but a little different. Notice one of the lines is just a little shorter, okay? The standard is that the longer line represents positive. That's the one thing that you sort of need to take away from that. If it helps, keep in mind these are both devices that can supply a potential difference, so it makes sense that their symbols would be somewhat similar. But the one with the shorter line is the battery. It's the one with the chemical magic inside. And also, just so you know, you might sometimes see this as a series of shorter and longer lines. That's also representing a battery, okay? Short and long combined, though, always means battery. There's more to put on this slide. I have all that space. I wonder what I was going to say. Maybe I should look at my notes and find out. Let's see, I said that, and I said that. Oh, look, there's an equation. You want to see an equation? No? It's kind of mean. You sure? It's kind of what we do here. You know, we talk concepts, then we talk equations. It's an easy equation. You're going to like this one compared to the previous chapters. We don't have, like, closed surface integrals, all that kind of stuff, right? This one is just this. I should make it large. Ooh. Q, that's a little too big, equals C times V. Q is equal to C times V. We know what Q is, charge. We know what V is, voltage or potential. And C, you might guess, is capacitance. Capacitance. The unit of capacitance is the farad. And I should make a couple of other points about this particular equation, just to make sure you don't get confused. From this point forward, we're sort of going to redefine what just the letter V means, okay? So we're going to say that V actually means delta V. Huh? Okay, so when I write V in this equation, we're just leaving out the delta part just for simplicity going forward because it would just convolute the equations. So just keep in mind that it means a difference in potential, and specifically it's talking about the difference in potential between the two plates of the capacitor. Okay? The potential difference between the two plates of the capacitor. All right? Also, I should let you know that this is a relationship between Q and V when I have a particular capacitor. I don't want you to make the mistake and think that capacitance is dependent on the charge and the voltage. It's just a relationship between the two. And I'm going to show you what we mean with the equation on the next page. Here's the thing. C, let's say, depends not on Q and V, but only on the physical characteristics of the capacitor. C is not dependent on Q and V. C will be dependent on the physical characteristics of the capacitor. Think about what makes up the capacitor. I take two conductors, I put them close together. How close? That's a physical characteristic of the capacitor. They have to be separated by an insulator. What kind? Is it air or is it something else? That's a physical characteristic. Also, each one of the conductors has a certain area. That's another physical characteristic of the capacitor. The way that I build it tells me something about its capacitance, okay? And I think if you just think about it, that makes sense, right? We're talking about storing charge. How much charge can I get on there, all right? The area is going to affect that. And how well the charge is repelled from the other side has something to do with the insulator that's in between, as well as how close the plates are together, okay? So let's take this to the next slide and find out something about the parallel plate capacitor in particular. And let me make sure that that's what I want to do today. We probably should, I guess. I'm going to do this slide, but then we're going to skip a few. How do we find capacitance for relatively simple cases? This is the slide that's going to connect us back to the last chapter, or the last two chapters. You'll see that there's one for finding capacitance for this configuration, the parallel plate capacitor. There's a slide here for, well, two conductors that are near each other in a cylinder, okay, so a cylindrical capacitor. And it turns out you can have capacitance even if I have two wires that are just nearby. It's still two conductors that are next to each other, okay? I want to do the first of these calculations for you just to show you how it works, and we'll come back to the others next week, okay? So how do we make a connection between what we had before and what we're learning about now? So we can say, first of all, from previously, last time on Physics 8b, I guess you might say, the electric field that exists between two plates like this. We've solved for this before. You can go back and look in your notes or look in the textbook, and you will see an equation for this electric field. It's equal to Q over epsilon naught A. We'll say for this setup between the plates. So we're not going to find the electric field. I want to show you how we can get from this electric field to an equation for the capacitance. So at this point, just accept that equation. Go back and look in your notes if you need to see where that comes from. And we also know that the potential is equal to minus the integral of E dot dl from some point A to some point B. You will notice over on the diagram, they've labeled the right plate as point A and the left plate as point B. So we're going to be integrating from right to left in that diagram. So let's see. We can rewrite this as minus the integral from A to B of E dl cosine theta. And what is theta in this case? Any thoughts? What's that? Is it 0? Could be 0. That's an option. Where's dl maybe in this equation if I'm integrating from right to left? I'm going to start drawing things. You might imagine something like this. dl, 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 dl. If I add up all the dl's, what am I going to end up getting? We would get L, which in this case is D. It's how far apart the plates are, okay? So dl is pointing to the left. E is pointing to the right. So what's theta? Theta would be 180 degrees, which means this whole thing is going to give me a negative 1. And then we're going to plug some things together. Okay, so at this point, we could say that I have V is equal to, well, just the integral from A to B of E dl, because we have two negative signs that are there. And then we're going to take this equation for this particular electric field and plug it in. that represents the electric field that is constant everywhere between the two plates. Okay, so we're going to integrate that electric field from plate on the right to plate on the left. So let's plug that in. Now we've got integral from A to B, Q over epsilon naught A, dl. And we already said that the integral of dl is going to give us the distance between the plates, but notice Q is a constant, epsilon naught is a constant, A is a constant, and then we've got A to B of dl, which gives me Q d epsilon naught A. Okay with that? Sort of a simple version of some of the problems you had in last chapter. So what does that mean? This is the potential difference between the two plates. That's really not what I want. I'd like to find out the capacitance of this configuration. So what we're going to do is use that with the equation from the previous slide. Q is equal to C times V, and solve that for C. So C is Q over V, and then we're going to plug that into the denominator. So now we've got Q epsilon naught A over Q D. And the Q's cancel. And that gives us C for a parallel plate capacitor. That equation only applies for the capacitance of a parallel plate capacitor. We'll see there's a different equation if it's a cylindrical capacitor. This is one that's going to serve us, well, quite a lot. We're going to use this one over and over. I want to talk a little bit about what it says, though. There's three things in there. Remember we said that the capacitance is based on the physical characteristics of this thing that we built. Look at the three quantities that are in there. Epsilon naught, that tells me about the space that's in between. In this particular case, we're assuming it's empty. There's an insulator there that's just essentially free space. Once we put an insulator in there, we'll replace epsilon naught with a different quantity that represents that insulator, all right? Area is the area of the plates. Notice if the area goes up, if the plates are bigger, so does capacitance. I think that just makes sense. It's almost like if the other classroom is larger, it can store more students, okay? More space, more charge. Also notice that D is in the denominator. If D goes down, the capacitance goes up. That speaks to how close the plates are together. If they're closer together, there's more of a repulsive effect of the charge on the other plate, which means it operates better as well. As I spread them apart, you can imagine, like, if they get far enough apart, like, I don't really have a capacitor anymore because one plate doesn't impact the other at all. They need to be somewhat closer together, and the closer they are, the bigger the capacitive effect. All right? Anybody have any questions about anything that we did there? Yeah. Yes. Yep. Yes. DL goes that way because specifically this problem was set up to integrate from A to B, and we decided A was on the right. We could have easily flipped that around, but then we'd get a negative potential, and, well, that's arbitrary. We could do that either direction. We set up the problem to get a positive potential difference. Yes? On these problems, yeah. Yep. From low to high will always give you a positive potential difference. Can I skip forward a few slides? Okay. This will help you with some of the homework if you wanted to get started on that over the weekend, or since we don't have class on Monday, like we've got some time here. So that'll help you with some of it. I want to talk about a few other things that will help you with some more of the homework, though, and at least get you started on that. And that is the case of actually taking these physical things known as capacitors and putting them into electrical circuits. We're going to connect them with other capacitors and with batteries and sort of see what they can do, see how they respond to each other. So the first thing I need to tell you is, well, what in the world is a circuit? How do we define an electrical circuit? You may have a feel for what it is, but let me give you a more technical definition. It is a closed path of conductors or in other words, wires, connecting various electrical devices. Closed path of conductors connecting various electrical devices. And I should add to that, one of which is typically a voltage source, something like a battery. A closed path of conductors connecting various things, which allows charges to move around from one thing to the other. Okay? If I don't have a closed path, well then it's kind of like, oh, well, there's no place for the charge to go, so it just doesn't even bother. Okay? And we're going to look at that idea in more detail in the next chapter. So you'll notice there on the bottom left, we've got a circuit diagram represented by a bunch of wires, which are just straight lines in this configuration. We've got 3 different capacitors that are labeled C1, C2, and C3. And we also have a battery or a source of voltage labeled as V at the bottom. Okay? These capacitors are specifically wired in what we call parallel configuration. These are capacitors that are wired in parallel. Now, you might look at this and say, oh, yeah, I see that. It's like, well, if I connect these lines, it's like, well, there's capacitor 1, and it has a line, and capacitor 2 has a line, and capacitor 3 has a line, and notice those 3 lines are parallel. That's not what is meant by parallel. We've only drawn it that way just because, well, it helps you sort of remember parallel. And also, it's just clean, okay? You might imagine if you were to actually go to the lab and try to build the circuit, and you've got like 3 of these capacitors, and you've got a battery, and you've got a bunch of wires, and you make all these connections, is it going to look like this? No, probably not, right? You're going to end up with something that more or less looks like this. You're going to be like, ooh, look, I've got a battery. And then it's like, oh, there's a wire going over here somewhere. And then you're going to be like, oh, here's one of my capacitors. It's kind of sitting up here. And you're like, okay, I made a connection. And then I'm going to make this other connection down here. And then you're like, I don't know what to do. Let's make a connection here. And then that's going to go like up there somewhere. And then you're going to like have one over here. And then it's going to connect there. And it's going to be all ugly and messy. And nothing is going to look parallel to anything else, okay? So don't make the mistake of thinking we're talking geometry here, because there's nothing geometrical about any of it. What is meant by parallel is this. Please don't draw that circuit. That was completely meaningless and was just to serve as an illustration, okay? What is meant by parallel is this, that all of these capacitors, we will say, share the same potential difference. They're in parallel if they share the same potential difference. Another valid way to look at this, and sometimes one will be helpful and sometimes the other will be helpful in trying to determine if something is in parallel, is that they have a common conductor on one side. That's not the word common. And a different common conductor on the other. They have a common conductor on one side and a different common conductor on the other. So we could go back and look at our diagram. Notice, we've got a wire that goes here. Look at it go. And yes, we've labeled like a point A. That's kind of nothing. Nothing's actually there. And we've labeled this other point, but like there's a wire that goes up to this one, and a wire that goes here, and a wire that goes there. There's no break in that wire necessarily. All of that is one conductor that's connected without any electrical device in between anywhere breaking it up. Okay? So that means that, yes, you could wire this exactly like it looks, right? You could try to be precise and be like, I want a wire that goes here, and then another wire that goes to this one, and this one. Or you could like literally be really, really messy about this, okay? And you could do something, let me draw another terrible circuit here. Like I could go up here and make a connection to that capacitor, and I could be like, ooh, let's do this. Ooh, like that, they still share the same conductor on that left side, okay? Even though, like, I've wired that nothing like what it really looks like in the diagram, okay? That's still a shared conductor. Notice on the right side, all of this is one unbroken conductor. It's a shared, a common conductor on the other side of the capacitor as well, which, yes, means like we could do something similar on the other side. We could be like, ooh, and we would get the exact same effect, okay? They just need to share a conductor on one side and on the other. That's going to look different in the lab and compared to what you see in the textbook, in diagrams. Everyone's circuit may build a little bit differently. You need to be able to get good at looking at circuits and sort of analyzing where the shared conductors are and where the same potential differences exist, okay? Are we all right so far? Yes? Not necessarily the same battery source, but that they have the same potential difference. So in this particular case, if we were to label a V1, V2, and V3, it's the same number. Whatever that number is, it's the same. Okay? Let's write that out mathematically, actually. I think that'll be helpful. In the 3 minutes we have left, we can finish up this parallel part. So when we say that they have the same potential, we can say that the potential difference on capacitor 1 is the same as the potential difference on capacitor 2. It's the same as the potential difference on 3. So I'm just going to call all of that V, which you'll notice is what we're using as the potential difference for the battery. Everything here in this particular circuit, it's like the simplest version of a parallel circuit, has the same potential difference across it. So we'll just use V for all of those. Here's the thing that's different. Even though they may have the same potential difference, even though they do have the same potential difference, they may store different amounts of charge. And you'll notice Q1, Q2, and Q3 are labeled. That's how much charge is stored on each individual capacitor. If the capacitors are identical, if they're the same, they'll end up having the same amount. You'll see that mathematically in a second. But if I have 3 different capacitors, they're going to have different amounts of charge go to each of them. Okay? Let's see how all that fits together. So we could say Q1 is equal to C1 times V, using the equation from a few slides ago. And we can write similar equations for the other 2 capacitors. Notice I'm not using a different subscript for V because V is common to all of them. But we have 3 different capacitance values and 3 different charge values that are being stored. We can say that Q total, this is the amount that leaves the battery and ends up on the capacitors, is equal to the charge on all of them added together. And then let's rewrite that with the equations above. C1V plus C2V plus C3V. Everyone still okay with those steps? Everything's making sense there, what we're plugging together? Perhaps, maybe. It's 4 o'clock. I'll have to leave that equation hanging. It's going somewhere. I'm sorry. You'll have to wait. Or read ahead if you're curious. We were talking about capacitors. We did sort of the hard part of this chapter already, which was dealing with finding equations for capacitance for different geometries, where we have to start with like what the electric field looks like and plug it into this equation for finding the potential difference given an electric field, and we have to do some sort of path integral, which the ones we tried weren't terribly difficult, but I'm leaving this one for you to try on your own. The solution to that is in the textbook in case you get stuck somewhere along the way. Where we left off on Tuesday was dealing with capacitors in circuits. And we talked fully through the first case where we can put capacitors in parallel with each other, and we talked about what it means for something to be in parallel. And keep in mind, 2 chapters from now, when we come back to other types of circuits, what makes something in parallel is still going to apply. They have to have the same potential difference across them because of the way they're wired, which means you have a shared conductor on one side and a different shared conductor on the other side of all of those things that are in parallel with each other, all right? From all of that, we were able to deduce this equation for an equivalent capacitance for multiple capacitors in parallel. And it turns out that if they're in parallel, we're essentially just adding capacitance. It's almost like we opened additional rooms for students to go into, or different additional space or surface area for charge to distribute itself across, all right? More in parallel means more capacitance overall. Who's got questions so far? Anything from Tuesday that's bothering you, still nagging at you? Nothing? No? You're happy? There's smiles over here. I don't. You're the guilty party. Uh-huh. Oh, yeah, that's no excuse. You can also get... That's, could be. No worries. We'll figure it out, though. So let's do the other case. In series, capacitors in series. Mathematically, this is the slightly more complicated one, but learning and understanding what it means to be in series is really as easy as it gets. In series, we could maybe just describe this as one right after the other. So you have one capacitor that's directly connected to a second capacitor that's directly connected to a third capacitor with no real options. One goes to the next, goes to the next. They are in series. So it turns out that series capacitors is sort of exactly backwards from parallel capacitors. In this particular case, we can say that they will all have the same charge. All have the same charge stored on them. And you see that in the diagram up there where, hey, look at that. Capacitor 1 has positive Q on the left side and negative Q on the right side. And then capacitor 2 is exactly the same. Capacitor 3 is exactly the same. And if we put 100 of them in series with each other, they would all have charge positive and negative Q on the two sides. Someone's chatting with someone right behind me. You're all in trouble. I don't care. Just keep chatting. I just want to read. No, I'll leave you alone. So one right after the other, they all have the same Q, but we could say that they may have different potential difference across each of them. Remember at this point also, when we just write V, we're actually saying delta V. We're just simplifying the terminology a little bit to make equations coming up a little simpler to look at. So they all have the same charge, but they may have a different potential difference across them. So let's look at those two things in the diagram. Why do they have the same charge? Remember on Tuesday we talked about sort of the process of charging a capacitor, how all of a sudden it's like, yay, more space for charge to go to, so charges run over there. And then that repels an equal amount of positive charge from the opposing side, and then it leaves, and I end up with a positive and negative side of a capacitor. Imagine what happens, though, if I put another capacitor right behind the first one. So we had this situation where it's like positives go here, and then positives leave this side due to repulsion, and then immediately run into another capacitor. It's almost like the second capacitor is experiencing the exact same thing that the first capacitor did, right? Now all of a sudden there's a buildup of charge on the second capacitor, which starts to repel positive charges from the other side of it, and so forth to the third capacitor. So it's like this chain reaction of one right after the other affects the next one, affects the next one, affects the next one, okay? So same charge on each one of those. How come they have different potential difference? We'll look at how they're wired and the fact that we have different conductors. So there's one conductor that's over here on the left side, and a different conductor that is connected between capacitor 1 and capacitor 2. And then there's another conductor that's connecting capacitor 2 and capacitor 3. And then, what color to go to now? How about this one? And then another conductor after capacitor 3 back to the voltage source. So they're clearly not sharing the same conductor on the first and second side of all of them. In fact, each one of them has a different pair of conductors that's connecting one side to the other. All right? So they all have different potential differences. Are we good so far? As good as you can be for a Thursday? The sun's out. Like, yay, finally, after what seemed like 40 weeks of rain. I thought it was never going to end, and I thought about leaving California forever because I was like, I thought I was coming to a place where it's sunny all the time. Maybe but East Bay. Like, I thought East Bay was better than the peninsula, and no. And all of a sudden it rained, and it was cloudy, and I was like, I should just move back to Boston. Not that that's better, I guess, but, find somewhere else. So thankfully it's sunny now, so we should all be happy on a Thursday. Does anybody have any questions about what I have up here about these two facts? Do you see why these are happening? Can somebody nod? Remember, you're allowed to lie. Like, even if you're not listening at all, if I ask a question, just go, yeah, that's fantastic. Yes, a question. Can I go over what?
How would they all have the same charge but have different potentials?
Let's see. So the potential I'm going to get to in the equation, which I think will make more sense in just a second. But as far as the charge, think about a chain reaction and how one capacitor charges. One capacitor charges by positives going to one side and repelling an equal number of positives from the other side, just because the two conductors are really close together. And then those positive charges hit the second capacitor and repel an equal amount, and then those charges hit the third capacitor and repel an equal amount. So Q is Q is Q is Q everywhere, all right? As far as potential differences, though, to help explain that a little bit better, you might get the idea that if I were to look at this conductor on the left and this conductor all the way on the right, there is some total potential difference between the left side of the battery and the right side of the battery, the high potential and the low potential. Somehow, through these other connections, I have to sort of get my way down to that lower potential. Whatever the potential difference is between these 2 points, plus whatever it is between these 2 points, plus whatever it is between these 2 points, has to be whatever the potential is between the total left side and the full right side, okay? In other words, we could write an equation that looks like this. We could say that V total, if you want, let's just leave it as V, since that says V, is equal to the potential difference across capacitor 1 plus the potential difference across capacitor 2 plus the potential difference across capacitor 3. Those individual potential differences have to equal the total. Otherwise, by the time I get to the other side of the circuit and I'm back where I started, I'd be at like a different potential, which you could think of it as being at a different height. That would be the equivalent of me deciding to like go around the classroom on these stairs, and by the time I get back to this point, I'm not on the ground, I end up like standing right here. That'd be a little creepy and weird. Still, now it's working. Weird. I think it's the banana. Has control over microphones. I don't know how or why. All right. Yeah, let me know if something goes out once again. For all those people out there who've decided to listen to this later instead of coming to class, I see you. I'm watching you watch this video right now. That's a little creepy, right? Because you know someone's watching it at like 2 a.m. Yeah, it's a pretty good slide, right? You like the slide? It's a nice slide. Look at that, capacitors and circuits, series circuits. Do you understand? You don't? Maybe you should have come to class and asked a question. Okay, I'm going to stop that now. It's just mean. So let's see. Let's step through this a little bit further. We could say since the charge is the same on every one of these capacitors, we could just leave a subscript off of that and use our equation Q is equal to C times V for each capacitor. So that's equal to C1 times V1 for the first capacitor, and that's also going to be equal to C2 times V2, and that's also equal to C3 times V3. Same Q for all, it doesn't need a subscript, but the capacitance times the potential difference should give me the same Q in all cases. So let's solve each part of that for potential and plug it into the equation right above. So let's say here we have V1 is Q over C1, and V2 is Q over C2, and V3 is Q over C3. Okay? And then we're going to use this and this together with, say, Q equals CV, and we'll say this is for the entire circuit. Q for the entire circuit is the same as it is for all the individual capacitors. C and V, though, maybe we can get to a total or equivalent capacitance, and V is that total potential difference all the way from the left side to the right side, all right? So first step here, we might write that this V is V1 plus V2 plus V3, so using that equation. And then we'll use this set of equations to rewrite it one more time. So that's going to be Q over C1 plus Q over C2 plus Q over C3. Okay? So let's see, what else can we do with this at this point? I'm going to divide by the C to get it over to the other side, and then we can factor a Q out everywhere. So we're going to have Q over C equals Q times 1 over C1 plus 1 over C2 plus 1 over C3. And then the Q's cancel, and I have a relationship of just capacitances, right? So the Q's are gone, and we end up with that relationship. For the equivalent capacitance, or the total, or the replacement capacitor that that could replace 3 capacitors in series with each other, it's the sum, the reciprocal of the sum of the reciprocals, if that made any sense, okay? Add the reciprocals, take the reciprocal one more time, and you get the equivalent capacitance. So it turns out that if I put capacitors in series, we end up reducing the overall capacitance of the circuit. Capacitors in series reduces the overall capacitance of the circuit. In fact, just try it with some made-up numbers. If you were to just try it where maybe C1, C2, and C3 are just 1, 2, and 3 farads and solve that for the equivalent capacitance, you'll actually get a number that's lower than the lowest one. So if the lowest one is 1 farad, you're going to get a sum or an equivalent that's actually less than 1. If I put more and more in series with each other, that number is going to continue to go down even farther. So putting more in series really doesn't necessarily help if you're looking for more capacitance. It's going the other direction. So you might start to wonder, well, why don't I just get the right capacitor and forget all of this, right? So maybe you need in a circuit a particular value of capacitance, but all that's available to you, even like online, you go shopping, you're like, I need this particular capacitor, and it doesn't exist. I need this small value. But you can easily, or maybe it's cheaper to buy bigger capacitors. Okay, so you could get those, and if you wire them up in series, just in the right combination, well, you could effectively get the capacitor you're looking for just by using multiple capacitors in series. Okay? Who's got questions? Yes. A fun fact?
Yeah.
I like fun facts. Go. can't think of anything off the top of my head. I agree. There's something about parallel. It's just like, oh, that's obvious. But series doesn't come across that way at all. I don't have a good way to explain it. Do you?
I think you can increase the distance between the plates.
See it as increased distance between the plates. The effect is certainly the same, but I'm not sure that I can see that intuitively. But I agree the effect is the same. Anybody else want to add anything? No? You all are extra quiet today. And extra starey. Like on top, like it's one thing to be quiet, but just sort of looking down. But you today is just this. It's really kind of scaring me a little bit. I feel like maybe all of you are involved here, and nobody wants to tip their hand. It's starting to worry me. Oh, I should just check. Let's see if she's written back. Nothing yet. If we don't hear from her by the end of class, then nobody leaves until you confess. Capacitors in series and parallel. So let's do a quick example, not terribly quick, of combining both of these concepts into one. So we're going to start by just doing the entire thing symbolically, and then I'm going to give you some numbers. 3 capacitors here. all at once? And 3 over 2c equals 1 over CEQ. And then we'll not forget that last reciprocal, so CEQ is going to be 2c over 3. Okay? Remember what we said, that putting things in series reduces the overall capacitance? Take a look at that result. Our individual capacitors are each C, but we have this one series combination, so the overall capacitance is 2/3 C. We've dropped it. Okay, there's less capacitance here than there would be otherwise. So let's take this with some numbers and solve for, well, sort of everything. Let's make a little room here. Ooh. Let's do that on the other side too. Why not? Just because there's absolutely no reason. And the mic is back now, isn't it? Man, that's weird. It's going to go out again. I wonder how I make it go out. I don't know. So let me give you some numbers. Let's say that the capacitance is 3 microfarads. Let's say the potential difference is 4 volts. And we are going to find, let's see, Q and V for each capacitor. So we want to find how much charge is stored on each and what the potential difference is across each capacitor. So let's start with the entire circuit. That's sort of where we are now. We've reduced the entire thing down where we just have one equivalent capacitance. In fact, we could redraw this circuit one more time, and it kind of looks, well, just like this now. We have a CEQ, and we still have this potential difference. So let's write Q is equal to CV for this state of the circuit where everything is put together. So we're going to use the entire potential difference. We're going to use CEQ, and that's going to tell me something about how much charge is going toward this CEQ that we've determined. All right? So let's see. CEQ is 2C over 3, and V, we said, was 4 volts. And I have an answer for that somewhere, unless someone has already calculated it and wants to tell me what it is. How about 8 times 10 to the minus 6? And that's coulombs. So you could think of that as, in a way, like the total amount of charge that's like moving into the capacitor system that's building up. If we step one level back, we know that capacitors in series have the same amount of charge. So we could say that this is also equal to the charge on the 2-3 combination, and also the charge on capacitor 1. So we've actually found one of the, 6 values that we're trying. We have that. Well, I could use capacitance 1 to find the potential difference across 1 as well. So let's do that right next door. So we can say Q1 is equal to C1 times V1 and rearrange that for V1. And we've got everything we need for that. So we've got the 8 times 10 to the minus 6. And what is the capacitance? They're all the same. It's 3 microfarads, so that's 10 to the minus 6 as well. So V1 should be 2.67 volts. So we know everything about capacitor 1. We knew its capacitance. We now know the potential difference across capacitor 1 as well as how much charge is there. So if we're looking back at the circuit, we essentially know the potential difference between this conductor on the right side and this conductor that sort of sits in between C1 and the combination of C2 and C3. We know the potential difference between those 2 points. So once we have that, let's see. Let's go back up to the top, and I'm going to use the 2-3 combination. We know everything about 1, so we have to step into the 2 and 3 together to find something else out. So we'll write Q is equal to C23 V23. You might remember when I introduced this equation, Q is equal to CV, it's like we can use it repeatedly in a variety of different ways. You can use it for the entire circuit at once, and you can use it for any part of the circuit as long as the Q, the C, and the V are all talking about the same thing. So you can't say use the Q for the whole circuit and then just use C1. That doesn't make a whole lot of sense. Just make sure that you're consistent throughout the equation. So here we're talking about Q equals CV for that 2-3 combination, and you might remember that right down here at the bottom, we know one of these two things. Let's just make this slide terribly messy. Look at that. We know Q23, and we also know something about C23 right here. So that means I have enough information to find V23. So V23 is Q23 over C23. I'm tired of saying 2-3. How about you? You're like, I haven't said it once. Are you tired of listening to 2-3? No? Boy, people are looking at you as if that was the wrong thing to say. 2-3, 2-3, 2-3. 2-3, 2-3. I should just lecture the rest of the time. Just use If it helps you a little bit, you could go ahead and pretend that there's a battery over here, although that's not necessary at all. They're just saying this is a little piece of a circuit that has 3 capacitors. What is the equivalent capacitance of those 3? I will give you a moment. Or 2 moments. Yes, talk to people around you. Get help. Help them. They look lost. You should really help the people around you. Yes. That's when you do the reciprocal thing. How come nobody sat back here in the corner? It's my new seat. This is nice. The 2 that I've circled, are those in series or parallel with each other? Start with that. What do you think? Yes? No? Questions? Can I stay back here? It's very echoey back here. I like it. Hello! Okay, I thought somebody would help me out there, but no, apparently not. Hello! Okay, if an echo said hi back after I said hello, that's when I leave immediately. It's a sad hi as well. So the 2 on the right are in series. One occurs right after the other one. So we combine them using the reciprocal thingy. So you get C over 2 for the equivalent capacitance of just those 2. Then I redrew the circuit such that the 2 on the right have now been combined, which leaves me with a parallel combination of what's left. One of which is C and the other one is C over 2. Add those together and you get a C and a half, if you want to think about it that way. 1.5 C. It's 3 C over 2. Okay? Any questions about any parts of that? Yeah. How do you know to start with series? That is a good question. Yeah. Look around, I guess. Is anything else clearly in parallel? So, for instance, if I tried to say that maybe this one and this one are in parallel, well, there's this conductor that is not the same as the conductor that's on this side, although they do share the other conductor on the opposite side. If you try that with the other two, well, they have a shared conductor on this side, but not on the back side of them. So that's the only combination in there that I can put together clearly, is that series. Yes? Say again, I'm sorry. Remember, in parallel, they have to have the same shared conductor on one side and on the other side. So if I look, you talking about these two or the other two? The other two, okay. This one has this conductor, which you can see kind of goes all through here, but that is a different conductor than the one there, okay? If I were to look at the other side, they do have the same conductor touching them, right? Let's take the same circuit and put some numbers in there. How does V1 compare to V2? How does V1 compare to V2? Equal, greater than, less than? And if you want to just bail out, there's your answer. Everything's zero. I don't care anymore. What is C1? What is V1? What's the numerical answer for V1? The potential across the first capacitor. Taking a look where I've drawn common conductors. 10, right? It's between greenish and pinkish, and that's the same across the 10-volt battery as it is across C1, okay? So I know that V1 is 10, so we could go ahead and even write that in if we wanted to. These are all 10 volts, okay? C2 and C3 are in series, which means they're going to have the same charge but different amounts of potential. But whatever that is has to add to give me 10 because just take a look at the diagram, right? We have green here, and down here we have the pinkish color, okay? So whatever this potential difference is, well, it's going to be less than 10. Agreed? Okay, because this one plus this one add to give me the total, which is 10. So we could say that our answer is that V1 is greater than V2. Okay, V1 is greater than V2. There's one more of these, I think. How about charge? How does the charge on 1 and on 2 compare? And based on the answer on the last slide, you should get to this one kind of quick. What's the answer? It's 2. Right? We already know that V1 is greater than V2. Just because C happens to be the same in this problem, they're all the same value, we can determine that Q1 must also be bigger than Q2. Okay? Ooh, lots of good stuff. Yes? You okay? A little scary? There's a lot of practice on this on the homework. So I've taught it to you now. It's now in your hands to sort it out and learn it. All right? none of you are repulsive. I don't know. I'm digging myself a hole now. But you get the idea, right? As more and more go onto the plates, there's a back repulsive effect that I have to work harder against to put more charge onto those plates, okay? So when we're talking about work, it doesn't take a lot of work to push the first few charges over, but with each additional charge, there's an incremental amount of additional work that's required for those later charges. Yes?
And again, this is a very kind question, but we can't, we wouldn't put like an electron in we wouldn't put the opposite charge on.
It's all the same charge on one side, but again, it's a buildup of charge. There's still positives and negatives on that side. There's just an excess. So when we say that the capacitor is, like this, plus, it's not to say that there's no negative charges there. There's just a deficit of negatives such that it's net positive. We're not removing all the negative charges. Mm-hmm. If we add more negative charges, that's going to make the potential lower, more negative. Yeah. Okay? So if we were to put this in equation form, let's do that. There we go. Make that go away. We need to add up all of that work to find out how much energy is stored on the capacitor. So we could write something like this, just based on what I wrote in that first statement. We could say that a little bit of stored potential energy is going to be the same as a little bit of the work that's required to move the charges onto the plates. And from the previous chapter, we know that this potential energy or work is equal to the potential difference, and we're going to write this as times dq. Potential times charge is an amount of work. And then to find the total amount of stored energy, we're just going to have to integrate this over all of the charges that go. So we'll say from 0 up to total charge Q. And then we're going to use our equation Q is equal to CV to write this voltage in terms of the capacitance that's there instead. So we could say that this is the integral from 0 to Q, and V is going to be Q over C, because Q is equal to C times V. So Q over C dQ. And then the capacitance is constant, so now we just have Q dQ, again from 0 to total charge Q. So that's going to give me 1 over 2C Q squared. Let's just simplify that a little bit. Or 1/2 Q squared over C. In terms of the capacitance itself and how much charge is on the plates of the capacitor, this is a measurement of how much energy is being stored by that particular capacitor. But we can take this equation and rewrite it a couple of other ways using that relationship once again. So we'll say using Q is equal to CV. We're going to plug in, first of all, for Q. So let's rewrite the equation that we had, 1/2 Q squared C. And then I'm going to plug this in for Q. So that's 1/2 C squared V squared over C. And one of my C's cancels. And then we've got CV squared over 2. So in terms of two other variables, the potential difference and the capacitance, that's how much energy is stored by a capacitor. We can flip one more time. So we could say that this is also equal to, plugging in for the capacitance is Q over V times V squared over 2. And then one of these V's cancels, and we've got QV over 2. So in terms of charge and potential difference. All the same equation, just depending on which two of the three variables for that given capacitor you might happen to have. Yes? Upper and lowercase q. Not really anything other than we're using Q to just represent some of the charge, and big Q just to be the sum of all the little q's. Both are just charge, though. Anybody else? Yeah. Potential energy, the negative of work. Yeah, we're just looking at magnitudes in this case. So if you want to write something like that, just to correct it. Good call. We can look at this energy one other way, though. Let me put a slide in here. I ran out of room. Add page below. And let's take that equation that we already had. U is equal to 1/2 CV squared. So one of the three versions of the equation we have for the stored potential energy on a capacitor. And we're going to plug in for both the capacitance and the potential difference, specifically, since we know something about this, for a parallel plate capacitor. Just so we can use some equations that we've had before. It turns out that you can do the exact same thing for other types of capacitors, and all of them end up with the exact same result. Okay, so we're looking at one specific case, but it applies to all. So C for a parallel plate capacitor. Back? No, it didn't work. It did. Well, that's just creepy and weird then. It says red now, though. Nope, it's dead. Nope, it's back. Wow, what a confusing mic. So epsilon naught A over D, we're going to plug that in for C. And you might remember that the potential difference across a parallel plate capacitor is the electric field times the distance between the two plates. So we're going to use those two things. So we've got 1/2 epsilon naught A over D and V squared. So that's going to be the electric field squared times the plate separation squared. So let's see. We can cancel one of these D's. And now we have 1/2 epsilon naught. And I'm going to put the E squared first times A times D. And I rearranged that specifically to put the A and the D together. The area of one of the plates times the distance between the plates. This is really the volume of the space between the plates. The volume of the space between the plates. So what we're going to do is take this equation. We've got U is equal to, let me rewrite it, 1/2 epsilon naught E squared times volume. I better do that because otherwise we're going to have V for potential and then everything's going to get lost and confused, right? And I'm going to divide both sides by volume. So we're going to divide by volume. So those cancel out. Now I've got potential energy divided by volume on the left side. That's really just a density for that volume of space that's in between the plates. So this thing is given this symbol, which is the energy density. And you'll notice that it's just equal to 1/2 times epsilon naught times E squared. The energy density stored in the capacitor is all about that insulator that's in between. So do I have free space or a vacuum or air or something that has roughly a permittivity close to that epsilon naught? And what the electric field is between the plates. You might even use this to think of this as the energy being stored in the electric field. Okay, an alternate way of thinking about it. You could think of it as energy being stored by the positioning of the charges, but those positioning of charges creates an electric field, so you could kind of flip it around and think of the electric field between the plates as literally storing some energy there for use later on. Okay? Energy density for a capacitor. Let's see. What should I add to that? Anything? Any questions? Now we have all this space down here and nothing to do with it. You can't see that now, though, can you? Anybody? Anything at all? Nothing? Yeah. We are going to use it in the later parts of this chapter, and also we're writing energy density to make this point that it's dependent on the electric field. Anybody else? Does anybody want to drill some windows into these walls? Like, just get started on that now, because the death that this room is. Question? Joule, that will work out to be joules per cubic meter. Joules per cubic meter. So it is literally a density. So we could write that at joules per meter cubed. Yep. Which brings us to a little change. Okay? So we've got 20 minutes left in class. I want to at least get through part of this dielectric stuff before we wrap up the week. But before we do that, I think I'm just going to pick a number in my head and see if I get anywhere. And if I call your number, you have to ask a question of some type or another. Are you ready? 64. Where are the numbers? I can't see them from where I am. They're completely... Who's sitting the closest to 64? It's you. So, you can ask me a personal question, you can ask a physics question, you can defer to this person sitting next to you if you want to just be mean, or you can tell a joke. If not a banana. Well, clearly, if not a banana. I don't really like fruit, which I know is kind of sad. But if I had to eat fruit, it would probably just be an apple. I mean, think about it. That's a good choice. Yeah? Apple? Apple fans? Yeah, apples are good. What do you people eat then? What is your favorite fruit? I don't know what happened. Strawberries. See, no, strawberries are weird. They got those little seeds on the outside. Isn't that creepy in a way? Like, I don't know. I guess you could slice all that off and just eat what's in the middle, but strawberry people? It adds character? What the seeds do? Why? What kind of character?
The strawberry part is the stem.
What are you talking about?
The red part of the strawberry is the swollen stem. Little seedlings are actually fruits and the seed are inside that.
So what part do you eat?
The stem.
You eat the stem and the seeds.
Yeah.
So the entire, like, meat of the strawberry is a stem. Yeah, I don't know. That's a weird thing to say. Yeah. I'm just going to go up here. There's really nothing to add to that. People in favor of kicking out anyone who makes bad jokes. Yeah, see, the people behind you want you both to leave. Everyone wants you gone. I don't know. Apples are good. I'm going to go with apples. Grapes I like. Other than that, I'm just done. Other fruits are just disgusting.
Whoa. Serious question. If you really don't like bananas, why is your shirt banana colored?
Yes, mustard. Ah, I think we can prove that. See? We'll just go down here and take care of this. Although apparently some people didn't like me saying that all the other fruits, besides apples and grapes, are just gross. You have other fruit? Pears? Oh, a pear is just like a disgusting apple. Yes? It's like an apple that went sideways. Yeah, that is not the same yellow. So, yeah. The elephant? What? There is an elephant on there. Who knew? Dielectrics. Let's talk about dielectrics. Dielectrics, you want to be a piece. It's just, that's fruit. Electric are really just a fancy way of saying we're going to change the insulator. So far, all we've had in between the plates of the capacitor is just air. Or if you really wanted to stretch it, maybe vacuum. We're basically just left it empty and said, we'll let that be the insulator that's in between, that's good enough. We can make capacitors better if we take other insulating materials and actually take something that's solid and put that in between the plates of the capacitor. It turns out that there are some benefits, and really I should break this into two parts. The first two sort of tell you a little bit about practically why putting a different insulating material helps. And the bottom two quantifies a little bit better what happens with the equations in the case of a different insulating material. So first of all, the idea that dielectrics don't break down, in quotes, as easily as air might break down. By breakdown, we're not meaning that, like, your capacitor is just chugging along and then all of a sudden it's like, and it broke down. Like, capacitors don't do that. That would be ridiculous. I should shut up, all right? Instead, we're talking about allowing charge to pass. In other words, if I turn the potential difference up high enough on a capacitor that only has air in between, that insulator can break down and allow charge to go through, much like what happens with lightning, as we mentioned in class on Tuesday. If the potential difference is large enough, even an insulating material might temporarily become a conductor and let the charge go across. A capacitor does nobody any good if the positives are allowed to go over to the negatives and everything neutralizes. It's not storing charge anymore. There's no charge separation. So this means I'm able to turn the capacitor up to a higher potential difference, which will allow it to store more charge without this risk of charge jumping across through the insulator. It allows me to have a higher V. And don't forget, Q is equal to C times V. If I can make V higher, I can push more charge onto those plates for a given capacitor. Yes? Oh, we're not there yet, though. That's point 2. I haven't said it. That means you weren't listening. Now you're in trouble. Get out. I'm just going to start kicking people out of class. Why not? That just sounds like fun. So number 2, we'll talk about number 2. The plates or the parts or the two conductors of my capacitor, we can actually get them closer together without a risk of them touching. If they touch, well, then the charge just goes across. That's the same thing as it breaking down. It's not storing charge anymore. But you might remember from our equation for the parallel plate capacitor that one of the ways to increase the capacitance is to lower D, the plate separation, to get those two conductors closer and closer together. By putting them closer together, I get a stronger repulsive effect on the second plate, which allows the capacitive effect to occur better. If I spread the plates far out, it's like, well, who cares if there's charge on one plate? It has nothing to do with the second plate because it's too far away. Putting them closer together increases the capacitance by increasing the repulsive effect. So if you think about it, it would be really nice maybe if I could just take air and leave it in between and build a capacitor. Dielectric is simply a fancy word for when we take something other than air that's insulating and put it in between the plates of a capacitor, okay? These top 2 points that I mentioned are sort of the physical reasons, at least the start of the physical reasons why it makes the capacitor better. It allows me to increase the potential difference, and we know that Q is equal to CV, so I'll get more charge on the plates by increasing the potential difference. And also it allows me to physically put the plates closer together. And if I do that, that increases the amount of impact one plate has on the other and increases the capacitive effect as well. Because you might remember that For a parallel capacitor, what is it? Epsilon naught A over D. So if I can decrease D, I increase the capacitance, all right? So again, that's for parallel plate only. All right? These last two give you a little bit of math as to what happens, what's the effect. And there's nothing complicated here. Just sort of take it and run with it, all right? Notice, number 3 says that it increases C by a factor K. This factor K is the dielectric constant. It's just something you look up in a table. It's different for different insulators, all right? Some work better at this than others. So what we're saying is that C is equal to C naught times K, where this is the capacitance without the dielectric. So take your original capacitor, put a dielectric in there, it multiplies the capacitance by K. End of story, okay? That's kind of nice. It's like the easiest thing we get to do all semester, I think, all right? The reason this happens is really because of what's happening with the permittivity. So notice we're replacing the permittivity of free space with the permittivity of the material. And the permittivity of the material is, again, related to how well electric fields are able to propagate through that material. So what happens is now we have epsilon is equal to epsilon naught times K. Okay? It's increased by the exact same factor, which you can see if you just went back up and plugged it into that equation, you can see it increases the capacitance by K. So everything is happening by a factor of K when we're dealing with dielectrics. On the next slide, most of this I'm going to kind of skip over and ignore because it's kind of just a proof more than anything. So I'm just going to go, whee, that was fun. Like, let's all enjoy that together. What do you say for the next one? Because I'm going to do it for the other box down there too. Ready? Whee! I did it backwards, didn't I? Oh, sorry. Ooh, there we go. Instead, I want to point out a couple of things here. Notice, number 1 is a capacitor with a consistent connection to a voltage source, okay? In the case of a capacitor that's always connected to a battery or some other source of voltage, whatever that voltage is across the capacitor plates is going to be held constant. That other thing, that battery, it again has a chemical reaction inside that's able to maintain the potential difference. So no matter what I do with the capacitor in that configuration, V is going to stay constant. So if I physically go in and say, oh, parallel capacitor, I'm going to push you closer together, or I'm going to pull the plates apart. Or I decide, like now I want a dielectric, and I decide to insert a dielectric in between the plates, I can make a variety of physical changes which will change charge and capacitance, but in that configuration, voltage is forced to be constant, okay? So we could say that any physical changes change the other things, change Q and C, but V is held constant. On the other hand, if I take a capacitor that I've already charged, the charge is on the plates, positives, negatives, they're ready to go, and then I disconnect it, and again, like now I have a capacitor that's potentially dangerous, be careful, like there it is, stray capacitor, and then I make changes. What happens now is that it's not connected to something that can maintain the potential difference, but the amount of charge that's on there is the amount of charge that's on there. In other words, Q is now going to be constant, but if I make any physical changes to the capacitor without, of course, like letting the charge out by discharging it, well, if I make any changes like inserting a dielectric, changing the spacing of the plates, or doing anything else, it's the other things that could change. So this will change V and or C. Any physical changes. Okay? You may have some questions on the homework that are kind of related to something like this. We've got some class questions coming up as well that are about that. All right? The things that we crossed out, again, are just proofs of this happening. It's fine that you don't know that. But I do want to talk a little bit about why. Or why, I think is the way that's read. All right? Notice, here we have a parallel plate capacitor without a dielectric on the left. We know that's what the electric field looks like. And then we're going to go through the process of sort of, sliding a dielectric material inside, which for some reason looks like a bunch of random little bugs that decide to all get in rows. Again, take this with a grain of salt. It's not this perfect, okay? But if you imagine charges that are in the dielectric that is neutral, even so, you still have positives and negatives that would like to align themselves with the electric field as much as they can. Different materials will be able to do that better than others. Here they're showing like a perfect case where it's like everything in there just goes whoop, and positive and negatives are attracted to what they're attracted to, and they're all perfectly in a line. So in the perfect case, you can imagine this results in positives on the side and negatives over on that side, okay? Again, not quite that perfect, but at least a tendency that way, so that we have a little bit of a positive buildup on one side and a negative buildup on the other. You can imagine that what that's going to do is create its own backwards electric field inside. That's kind of fun, okay? So we could say reverse electric field in the dielectric. So now I've got the electric field that's being generated by the plates, and then some smaller electric field that's going the opposite direction in the dielectric material itself, such that in this whole region inside now, the electric field has dropped. There's less electric field than there was just a moment before. So in other words, we could say a couple of different things. Let me go down here to my notes to make sure I say what I want to say. You might remember that, at least in this particular case, V is equal to E times D. We have a constant electric field. You can think of it as, if I move the D underneath, the potential difference divided by the distance between the plates is the electric field. So for this case, we have an equation that looks like that. We already learned that the potential essentially goes down in a way that allows me to turn this up. What's happening in this equation is that basically everything is getting divided by that dielectric constant K once again. So now, if we write these as maybe V zeros, we could say that the new electric field is the original electric field divided by the dielectric constant, so it drops. And also, we can say that the new potential difference is whatever the potential difference was before, divided by K. So both of those go down when I put in the dielectric, which again allows me to sort of like, you can kind of think of like, ooh, now I can turn things back up and get it where it was before without as much potential difference as what I had before. All right? How does that come together in the equation? Remember that C is equal to Q over V. Ooh, plug that in down there. Let's say that's V naught. And now we have Q is equal to V naught over K, which is just KQ over V. And you see that we've multiplied it by a K. The capacitance has increased by a factor of K because of the potential dropping by a factor of K. And that's happening because the electric field was decreased by a factor of K. End of story. Da-da-da-da. Yay. You okay with that? You can accept it. You don't really need to know anything more. All right? So I'm going to go back many slides. Where are we going to go? I like these slides. These slides are just jam-packed with information. Look at that. Wow. Some of the most dense slides we've had all semester. I like it. But we're going to go before that. Back to this thing, okay? This is very much like one of your homework problems. I want to go ahead and work this for you to help you get through that homework problem quickly. We're actually not going to do the next slide, but we are going to answer the questions that are after that. And then we'll know everything we need to know about capacitors for now. So, finding capacitance for something that's not a parallel plate capacitor. We are, again, going to use the equation we used on the previous slide. Let's see. What are we going to do? We're going to say that the potential difference, which, keep in mind now, we're just calling that V because we're getting rid of the delta because when I'm talking about circuits, it's just a bit too much, okay? So that's the same thing as V, and it's equal to negative the integral from point A to point B of E dot dl. What we need in this case is an equation for the electric field inside this cylindrical capacitor. Now look at the diagram on the right. What do we mean by a cylindrical capacitor? Essentially, we have a cylindrical shell, if you want to think about it that way, with like a wire that's passing down the middle, both of which are conductors. So that if I look at the end of this, it looks something like this. We've got this wire in the middle, all of it positively charged, and those charges will live on the exterior surface of that wire. And then we have negative charge on the inside of the exterior shell, okay? That gives me a positive electric field that just goes from positive to negative as expected. We've solved for this electric field before. Go back to Gauss's law stuff. We just had like a line of charge, and we used a cylindrical shell and found, or a cylindrical Gaussian surface to find the electric field outside of that. So we already know this equation. So I'm going to say from before. Although it'd be nice to like start from the beginning, right? And be like, let's find the electric field, and then let's find the capacitance from that. I'm not going to do all that. You can go back. It's in your notes. The electric field looks like this. It is 1 over 2 pi epsilon naught times lambda, the linear charge density, over r. Or we could rewrite that as 1 over 2 pi epsilon naught times q over L r. Q over L is just the linear charge density. And then we're going to plug that into the integral, and then we're basically going to be done. Okay? So let's take this and put it in there. So v is equal to negative the integral from a to b. And if you look at the diagram, a is the negative part, which is the outer shell, and b is the inner one. So we're going from low potential to high is the direction of integration, which will give us a positive change in potential. Okay? So let's see. Let's plug that in and see where it gets us. 1 over 2 pi epsilon naught q over LR dl. What is the L direction in this particular case? Zooming in. Ooh. Where is dl if I'm going from A to B? How about something kind of like this? Does that work for anybody? We're just going directly perpendicular from that exterior shell toward the inner wire. So actually that's in the radial direction. Okay, so I'm going to go back in this equation and replace that with dr. Right? Our dl this time is in the radial direction r. So a bunch of stuff there is constant. So we can pull out the q, the amount of charge is constant, the 2 pi epsilon naught, and the L are all constant. And then we're just integrating 1 over r dr, which is the natural log. Let me pause for a second. Let you absorb. Just let the beautiful physics wash over you. It's like a nice shower of wonderful physics. In the back. If L, let's see. That is an issue, isn't it? It's a mixture of terms. Let's do this. Let's call this capital L. And I think that'll clarify a little bit. Okay? So capital L is the length of the cylinder. dl is the direction of the path of integration. Ooh. There we go. I think that's everything now. Yes. Okay? So L is the length of the cylinder, which is related to the charge density. Okay? Little l is about the path of integration. Okay? Which ends up being whatever that distance is between the outer shell and the wire itself. Right? Good question. I hate it when symbols get all mixed up. That is totally my fault. So this thing here at the bottom, from A to B, we're actually, now that we're integrating with respect to dr, then we could say that this is from RA to RB. from the outer radius to the inner radius. And then what are we going to end up with? Let's see. We're going to have Q over 2 pi epsilon naught capital L. Oh, how many times is there this capital L there? There it is again. Times the natural log of RA over RB. And things have flipped upside down to get rid of the negative sign. So we have two negatives there that cancel out. That is the potential difference between the outer and the inner conductors. What's the next step? What did we do next to find the capacitance? Stunned silence. What was it? C is Q over V. So we're going to use that equation and just plug that in, okay? And that'll give us an equation for the capacitance of a cylindrical conductor, or a cylindrical capacitor, and then you can use that equation to help you with that particular homework problem. So what in the world does that look like once we put that in the denominator? So Q's are going to cancel out, and I'm going to end up with 2 pi epsilon naught L in the numerator, and that's over this. Something like that. Let me make sure I wrote that down right. Yes. Okay? Notice, when everything is said and done, the capacitance equation is only dependent on physical things about the capacitor, as it should be. How long it is. Epsilon naught is about the insulating space in between. RA and RB are the literal radii of the physical conductors that are there. Okay? When we're dealing with capacitance, you should only have physical variables that are in the particular equation. Okay? Any questions? We're almost done here. Yeah.
You inputted the E, which Gaussian surface are we looking at? As like the whole thing? With the...
That would be like with a Gaussian surface here. Okay? Because we're only trying to find the electric field in between. I'm not really worried about what's happening outside. Anybody else? Anything in there that's bothering you? Confusion? Well, I'm going to move on then. Yeah, we're skipping that one, which I think brings us to like 1, 2, 3, 4 questions, and then we're done with this chapter, and we're going to dig deep into chapter 9. So, capacitor C1 is connected across a battery of 5 volts. An identical capacitor C2 is connected across a battery of 10 volts. Which one's going to have more charge? What's the answer? This is the same. So the one with more voltage, more potential difference, results in more charge on that particular capacitor. So we could say here number 2 is the answer, all right? If I connect it to more potential difference, that pushes more charge onto the capacitor plates. So let's see. What must be done to this parallel plate capacitor to increase the amount of charge it can hold? Notice it says constant voltage, which means we're maintaining this connection to the battery at the bottom. So what are the physical things you can do to increase Q? Something's funny. Wonder what it is. I don't need to know. What's that? Hi. Not much. I'm just hanging out, you know. So let's see. We can increase the area. If you go back and look at the equation for parallel plates, epsilon naught A over D, or decrease the separation of the plates. So 1 and 2 will both increase the capacitance, which increases how much charge it can hold. What about this one? You'll notice an error. It says a voltage of 400 volts, and then down here it says 12 for some reason. I don't know what's going on with that. Let's just get rid of this. It's staying connected to the battery, which means 400 volts is going to stay constant, okay? If I double the plate spacing, what happens? Ooh, ooh. Ooh. 3 or 4? All at once. More of you. You can do this. 3, right? Charge goes down because it's not as good of a capacitor now because I've decreased the capacitance. So the charge decreases, which brings us to the last slide of this chapter, which has the exact same mistake. Ignore that 12 volts down there. It is charged to 400 volts, then disconnected, which means that Q will stay constant. And this time we're going to change the plate spacing. We're going to double how far apart they are. So what's going to happen this time? What do you think? Say a number. You're not sure. Or you just don't want to tell me. Or you have no idea what we're talking about. Which one is it? Who in the world knows? 2? Are you sure? Look at those 2 equations. What's going to happen? So we've got half of the capacitance because we're putting a 2 there. And if I have half the capacitance, that means we divide by 2 here, but have to multiply that by 2 to keep Q constant. Whoa, which gives us 800 volts. Okay? Again, it's all about whether it's connected to the battery or not, and which one of our 3 variables stays constant. The others are going to change in response. Okay? We are done with chapter 8. Go us. Be more excited. So let's see. We had talked about capacitors with dielectrics. Remember that a dielectric is just this idea where we take something other than air and put that in between. Uh-oh, yes. Many difficult questions. That's hard to say at this point. So I can tell you this. Let's see. Where did we cut off last time? So we ended thermodynamics. So 21, 22, 23, 24 for sure. Probably 25 as well. Simply because it's short, we'll definitely finish it like at the start of class on Thursday, and then the exam's not until, out there. Plus it's a sort of a weak chapter, yeah. It should all be just like last time, yeah. Also, I should probably tell you while we're on the topic, thank you for distracting me, both of you. Yeah. I'm welcome. Are you sure? The exam average was high on the first exam. It was much higher in this section than it was in the other, and I didn't look at the other exams, so I don't know if it's just, you're just smarter. That could be it. Or the other exam was like crazy harder. I don't know. I didn't compare them. So I don't know. I haven't looked at that either. That would be interesting. So I can tell you this. The second exam is going to be harder overall. Because at the end of the semester, all of the letter grade divisions are sort of based on the performance of the entire class. And if exam grades are too high, it could result in a negative curve because I'm only allowed to give so many A's. And I don't think anyone wants to be like, I got a 96. Why did I get a B+? That would just suck all the way around, don't you think? So we don't want that situation. It's better that it's like, I got a 78 and I got an A. Like, you just feel better about that way than the other way, okay? So this second exam is going to probably be significantly harder than the first one. So just prepare yourself for that. If you're also wondering, like, we cover thermodynamics in this class kind of, I don't know, sort of lightly. We talked about a lot of things, but didn't go terribly deep on any of it. With the electricity and magnetism, it's more the focus of the class, and we're just treating it more seriously overall. Our coverage of electricity and magnetism is more in-depth than thermodynamics, so it's natural that the exams will be harder as well. Okay? Plus, I have to make it a little harder also. Yeah.
Are there any review sessions celebrated?
That is a good question. All of that is supposed to happen, but the timing is a little off, and I haven't heard any official news yet.
So it's still the Tuesday after.
Yeah. Yeah. Would anybody come to a review session during spring break on the weekend? Who says yes? Wow, heck yeah, even. Wow, that's impressive. So there would be some. I wonder if maybe we'll do one because attendance could be down instead of doing 2 sessions or something. I don't know. I'll let you know as soon as I find out. Or Elon will let you know as soon as he determines such things. Any other questions that are exam related? Anything else you want to say to distract me from talking about dielectrics? Yeah?
Is the other classes different? You've got different things?
Yeah. Should be. Yeah. Nothing else? Okay. Dielectrics just make the capacitor better. That's sort of the end of the story on dielectrics. We talked about that from a practical perspective in the first 2 points, sort of physically what happens to make the dielectric improve the capacitance. The bottom 2 look at the really sort of weak mathematics that tells us what the effect is on the capacitance and how that's related to the effect on the permittivity, from the permittivity of free space to an actual permittivity of the material. We jumped over this slide, which I'm about to do in a second, but just for sake of review, the why behind all of this is that the dielectric material has an electric field inside it that's sort of induced by the external electric field, and it's in the opposite direction and weaker. So we get a cancellation of part of the electric field. The electric field in between the plates drops because of what's happening in the dielectric material and specifically on its surfaces. So we ended with what's happening in the relationship between the potential difference, the electric field, and the distance between the plates. If the electric field is dropping, of course, the potential difference between the plates has to drop as well. And don't forget this V equals ED only applies to this situation. This is for a parallel plate capacitor. Yes, sir? The dielectric in general will be an insulator. So it's like we're going from having an insulator that's just air to stepping to something that's more serious of an insulator, something that's more insulating. Anybody else? No? Can I go back a slide now? Yes? Just say yes, because I'm going to do it anyway. You might as well. Yes? Okay. All right. This is... Hello. Are you alive? Are you out there? Only these people are alive. So what about in the back? That was just sad. You didn't see like the hand motions I saw that went with that. There was like, woo. And then over here we've got like... I'm like, yeah, that's just not working for anybody. So let's talk about what happens in 2 different cases when I insert the dielectric. So notice in the top case, we have a capacitor that is going to be connected to a voltage source, and it stays that way, meaning that it's forced to have the potential difference that the battery has, and we're not going to allow that to change. So in this configuration, the potential difference between the 2 plates is a constant whether or not I put a dielectric inside. So we start on the left side with no dielectric, which means that the potential difference gives rise to a charge Q between the plates, and we're going to use a 0 subscript to indicate that we're not having a dielectric at this point. Okay, so you might divide those 2 things, and you'll see that the capacitance without the dielectric is just the ratio of the charge without the dielectric to the potential difference without the dielectric. Okay. Once I insert the dielectric material, and you can see that's happened here with this fancy bit of graphics, someone drew an orange box and put it in between the plates. Well, since the voltage is a constant, it's the charge that's going to change. And you can see that reflected in this equation, again, by this factor K, the dielectric constant. So the amount of charge on the plates increases when I insert the dielectric material, which, of course, that just represents like, oh, it's a better capacitor now. For a given potential difference, now it's storing more charge than it was before. So Q is now equal to K times the original charge, Q naught. And if we plug all of that together, we could, let's write something like this. We could say that our new capacitance is our new charge over the potential difference. That's right here. Just ignore this. I'm rewriting it because I want to add a step. Say, just ignore that. Don't worry about it. It's fine. Again, just ignore it. Just make that go away. Just scribble that out. Are you done scribbling? Okay, good. So our new charge, right, is K times Q naught. And you can see that this thing is exactly what we had over here. Whoa, right there. So our new capacitance is just K times our original capacitance. So you can see that the effect of an increase in charge gives us the equation we had before where we say that the capacitance is just increased by a factor K. Everything there fits together. Does it work, though, if I have a charged capacitor that's disconnected? A charged capacitor that's disconnected. So you can see in the bottom sequence, well, the left-hand side of this is exactly like what we had before. We're going to start by charging the capacitor without a dielectric, and we can say that the capacitance is just Q naught over V naught. Okay, it has charge Q naught at this point. Then we're going to take that capacitor and disconnect it from the battery. So this time there's nothing forcing the potential difference to remain the same. Instead, what has to stay the same is the amount of charge that's on the plates. It has nowhere to go. The amount that's there is stuck. I can't get any more, and I can't lose what's there. So the charge on the plates stays constant when I insert the dielectric. Something else has to change to reflect the increased capacitance. So still at this point, we have, well, the capacitance is Q naught over V naught. All I've done from the first step to the second is remove it from the voltage source, from the battery. And now, once again, we're going to do this very fancy artwork of inserting an orange block. Isn't that beautiful? And this time, the charge can't change. Q0 is going to stay Q0. It doesn't get multiplied by a factor this time because the charge can't go anywhere. Instead, the voltage must drop. And we can see that that's going to give us the exact same equation by doing something quite similar. So now the capacitance is Q naught over V naught over K, which just gives me K times Q naught over V naught, which is K times the original capacitance. So in both situations, we see that either an increase in charge when I have a constant voltage or a decrease in voltage when I have a constant charge results in a multiplication of the capacitance by K. Everything fits together. You got questions? Do you understand? Is everything happy? Are you alive? Anybody behind me here with questions? You didn't expect me to spin around, did you? I shocked you. How about you behind me over here? You have a question. Yes.
Could you explain why the voltage goes down if we disconnect the charge or disconnect the battery again?
The voltage only drops after I insert the dielectric. So when I first make the disconnection, the potential difference, the voltage stays exactly the same. The voltage is dropping essentially because it gives us this end equation. The result in the increase in capacitance is coming from a drop in voltage because of this. The next slide. All right, so the reason the potential is dropping is because the electric field is dropping. The capacitance doesn't remain the same. The charge remains the same. Okay? So it's a sequence of things. When I insert the dielectric, it ends up inducing this charge on the two sides of the dielectric material itself, which subtracts from the electric field. If the electric field drops, well, then the corresponding potential difference drops. And if all of that happens, the capacitance increases. All right? So all of these things we learned about in the last 3 chapters, it's all kind of connected together here. Electric field, electric potential, and how that affects charge on the plates of a capacitor. Okay? Other questions? Anybody? Anything over there? Yeah.
So you can change the amount of energy stored by moving it
Yeah. Yeah. And we're going to talk about that in an example problem in just a moment. But yeah, by inserting or removing the dielectric, you are changing how much energy is stored. Yeah. I want to add to this slide a little bit. We didn't finish everything that I wanted to talk about here. So we did discuss the idea that the electric field is dropping because I have a subtraction of electric fields, but we can write some equations to sort of spell that out better. So let's say that E sub D is the net electric field with a dielectric. The net electric field between the plates once I've inserted the dielectric, and it's going to be equal to the original electric field. Uh-oh, my D and my O look identical. Huh. That is a bit of a problem. I actually wrote them differently, but they didn't come out different. So let's try this again. Let's get rid of this one as well. D. Maybe I should write a lowercase d. Does that help? Maybe it's better. And then an O or a 0. That's different at least. So it's the original electric field that was between the plates before we put the dielectric, minus what's in the material itself, that backwards electric field. Let's call that E induced. So this is the backwards electric field in the dielectric. So we subtract those two and we get the final net electric field. So let's rearrange that and solve for the induced electric field. So that's going to be E naught. Oops, I left one part of this equation out. And this is E naught over K from here. Whoa. So now let's solve for E induced. Gives us something like that. And just for simplicity, let's factor out the E naught. Okay, so let's hang on to this equation. And we're also going to go back and use this equation in just a second. Okay? So we've got an equation for the final electric field, and then we've got an equation for the electric field between the two sides of the dielectric that goes backwards. Okay? I have some space here on a new slide next door. So we can say that the original electric field, again, is coming from the charge on the plates. And that's going to be equal to the charge density on the plates divided by epsilon naught. This equation should come from a previous chapter. I can't remember if we did the problem in here or you did it in the homework or in discussion, but somewhere you found the electric field from like an infinite plate of charge. We used Gauss's law to find that. It gives us this equation. Okay, it's sigma, the charge density, divided by epsilon naught. So I can rewrite that charge density as the charge on the plates divided by the area of a plate, and we'll keep the epsilon naught around. And we can do something similar for the charge on the dielectric that's causing the induced electric field. So E induced, this is from charge on the surface of dielectric. And that's going to be equal to an induced charge density divided by epsilon naught, or equal to Q induced over area epsilon naught. So let me draw a quick picture here since we don't have one on this screen. So we've got one plate plus, we've got this dielectric material that's inside. And we essentially said that you're going to end up with sort of some net charge buildup here. And then we've got our negative plate. That is like the worst parallel plates ever, but you get the idea. All right, so these charge densities are positive and negative sigma. These charge densities are positive sigma induced and negative sigma induced. A is the same everywhere. So the electric field is clearly being created by certain charge distributions or charge densities. There are some names that are given to some of these charges. So the charges that cause the charge on the plates, sometimes this Q here is called, let me make sure I get it right, the free charge. Free simply because it's free to move around. It's on a conductor. So the free charge on the plates of the conductor in a capacitor, the free charge. This is sometimes called the bound charge. It's bound because it's happening on the surface of an insulator where it's not really free to move around so much. Free charge and bound. That always works, right? Come back. Yeah, that's going to last for... Put it in my front pocket? I guess I could. Then I'll find myself leaning the other way, surely, because I'm just dumb like that. I wonder if it would go off if I lean the other way. So we're going to go there now? I don't know who you said that? Yeah. It's not going to work. That's nice. And it's still working. Thank you. Apparently I'm an idiot. You know, what I'm going to do. Who knows? So let's take these two equations and plug them into the previous slide, those boxed equations we had there. So let's see. Sigma induced over epsilon induced. We're going to take this and plug it in. Oh, where is it? All the way down here. So we can write sigma induced over epsilon naught equals sigma over epsilon naught times 1 minus 1 over k, because we had E induced equals original electric field times 1 minus 1 over k. And now we can cancel out those permittivities. And we have sigma induced equals sigma times 1 minus 1 over k. So a relationship between the two charge densities. So the charge density that's there on the plates is directly related to how much charge density you get induced on the dielectric. And of course it makes sense that would be connected back to the dielectric constant itself. We could do that one more time, except instead of using the charge densities, let's actually use Q to find out something about how the charges are related. And if we did that, we're going to get a very similar looking equation, which would be Q induced equals Q times 1 minus 1 over K. And keep in mind, K is always going to be greater than 1. So because of that, Q induced is always going to be less than Q. I think it makes sense that there shouldn't be as much charge building up on the surface of an insulator as on the plates of the conductor. Well, because one's an insulator and one's a conductor. The charges can't move around and respond directly as it would if I put a conductor next to a conductor. Okay? So the induced charge is always going to be less than the charges on the plates, which gives rise, of course, to less of an electric field. It's not a canceling effect. It's just a partial canceling effect. All right? Who's got questions, complaints, thoughts, comments, anything? Microphone is still working temporarily. Nothing? Okay. I'm going to add another slide. There's a couple of quick examples that I want to do. Actually, I have the slides here. I just didn't give them to you. There we go. A couple of examples from the book just to point out how some of this stuff fits together. I will paste these slides back into your set of slides so that you'll get them in the post-slide version. All right? So first of all, a really, really simple problem where we're not really going to do all of the math and everything, and I'm going to just give you the numbers at the end. I just want to sort of work through all of this to show you something right at the end of the problem. So the whole point of this is right at the end. We're going to start with a parallel plate capacitor that is charged. So you can see it's filled with a dielectric and fully charged. So we're starting in state A. Then we're going to remove the dielectric and see how all the quantities change. Okay? You can see the list here. Find the capacitance the charge, the electric field strength, and the energy stored in the capacitor in both of those states. So we can start here with, we'll say, a charged capacitor with a dielectric. And we are going to find C, and what else? Q, and E, and the energy. C, Q, E, and U. So, first of all, the capacitance in a dielectric is given by K times epsilon naught A over D, at least for a parallel plate capacitor. And they gave you all of those numbers. I'm not going to bore you by writing those numbers out. You should get 3 times 10 to the minus 8, and the units of a capacitance are farads. Once we have that, we can find the charge that are on the plates of that capacitor. So we have C from just above, and they gave us V. Where is V? There's V. And we'll bring that down. We'll put that there. Ignore me, it's okay. You should get 3 times 10 to the minus 6 because you're just multiplying by 100. And that's charge in coulombs. Let's see, the electric field. We can use the relationship to the potential difference and the separation between the plates to get the electric field. So that's just going to be V over D. So we have 100 for the potential difference. And D is up there somewhere and also given, I think. I don't see it. Where is it? Ooh, 4 millimeters. I crossed out part of it. This is turning colorful. That should give you 25,000 volts per meter. And then finally, once we have that, you can pick one of the equations for the energy that's stored in a capacitor. You had 3 different equations, just depending on what information you have. I'm going to use 1/2 CV squared. And we have C and V, and for that you should get 1.5 times 10 to the minus 4 joules. So notice this number for the energy that's stored when the dielectric is still there. We're now going to sort of reach in, not remove any charge, not get shocked, hopefully, and carefully remove the dielectric and just see how all 4 of these quantities change, okay? We need to make sure that the numbers that we end up with make some sense, okay? We know that the capacitance should be better when the dielectric is in place. So, part B, after the dielectric is removed, we are going to find the same things. After the dielectric is removed, so we could call these C naught, Q naught, E naught, and U naught. So the first one is just going to be C divided by K, rearranging the equation we had before. So we'll use this C, and K is given up there somewhere. It's 3.4. Let's just go ahead and make a mess of these slides. What do you say? Yeah, I know. I kind of know how this works in this class. There's like, I don't know, like 10% of you who are like, well, that's kind of goofy and amusing. There's another 10% of you on the other end that's like, just stop. Just tell me the numbers. There's a kind of a 10% that kind of lives somewhere just inside that 10%. It's like, you're messing up my notes. Quit it. You're going to post these slides. They're going to look terrible. It's going to be the worst, and you're just confusing me. I get that. And then the rest of you are just kind of like, what time is it? It's good. So, can't please everyone. What are you going to do? So let's see. What is this value of capacitance? That should be 8.8 times 10 to the minus 9 farads. Notice that's less than the number we had with the dielectric inside. So good so far. That makes sense. What about Q naught? Any thoughts there? Don't think too hard. Yeah? That's too hard. Thinking too much. Take a look at the problem up there again. Take a look at these pictures. Yeah, it's the same. It's not connected to a voltage source, so Q naught is the same as Q. The amount of charge that's there is trapped. So that's 3 times 10 to the minus 6. Let's see. E is going to be, I've got this all reversed. Let's see. E, let's fix that a little bit. E naught is what? E divided by K? Does that sound right? Or do I have that backwards? Other way around, right? There we go. E is E naught over K, and we're solving for E naught. Like so. E naught is KE, not kinetic energy. So let's see. K is 3.4. That's up above. We should switch back to that color and do this. Finish that up. And E we had before is 25,000. So this electric field is larger, and you should get 85,000 volts per meter. So we have a large electric field. When the dielectric is in, the electric field is less. So that makes sense as well. And then finally, at the bottom, we've got the new energy that's stored. So I'm going to use 1/2 C naught V naught squared. But I don't have this new value of potential difference yet. So we could rewrite this as C naught times VK squared. And that should give me my new value of potential difference in there. Once you plug those numbers in, you get 5.1 times 10 to the minus 4 joules. And please tell me if that makes any sense. Yeah? Exactly. So notice, our new energy stored is bigger than what was there when I had the dielectric in place. That energy had to come from somewhere. That energy came from you. All of you reaching in, pulling out the dielectric. It took some effort. It took some work to actually pull that material out, which, well, that energy had to go somewhere. It's now being stored in the capacitor itself. If you go back to the previous slide and look at what's happening here, notice there are negative charges up against positive charges on the surface of the dielectric and on the plates of the capacitor. That's an attractive force, which means the dielectric material, once it's in there, wants to be in there. Like it's going to be somewhat attracted to the plates of the conductor itself, so it's going to take some effort to remove. Okay? Any questions about this problem before I do one more? Yes? Q stays the same because it's not connected to a battery in this case. So there's, it's fully charged and then the battery is disconnected. Okay? Yeah?
Are there materials with permittivity less than
Materials of permittivity less than free space. The standard answer is no. Whether there's some sort of cutting edge research where someone's found something exotic, I'm not up to date enough on that. I will let you look around yourself. Anybody else? Good question. There's something about a permittivity less than free space that makes me think of the speed of light being greater than c, which seems to be a bit of an issue. So let's see. One more problem. A dielectric partially filling a capacitor. Which is really the way we've been drawing this all along, but mostly just for the sake of being able to see the different materials that are there. But in this problem, we literally are filling up half of the space. So you can see that for some reason, dielectrics are always orange. I'm not really sure why that happens to be the case. It is 1 millimeter wide, while the separation between the plates is 2 millimeters. So it's filling up half of the volume there instead of all of the volume. So we're going to try to find a few different things, and I'm doing this problem just because of one of the parts I think is a little bit interesting and a little bit different. So the other parts of the calculation are going to be quite straightforward. So let's write those down quickly. Look at all those letters. A, B, C, D, E, F, G. There's a lot of parts to this problem. I think that, this is nice. This whole row is almost empty. Why are you here? You should move. And then I could pace back and forth on this row. That'd be fantastic. How are you all? Good? You're still good. Nothing's changed. So you were good at the start of class, and you're still good. So I should just let you tell me if you think it bad, if things go sideways? Okay. I'll stop asking then. I'm done. So let's see, part A. What is the initial capacitance of the air-filled capacitor? Well, we know how to calculate that. It's nothing hard. So that's C0 is equal to epsilon naught A over D. Let me give you that number. You can double check me later in case you're worried. Part B says the charge on each plate before the dielectric is inserted. So, well, that is Q naught is equal to C naught V naught. We have all of those numbers. That should be 1.66 times 10 to the something I can't see. I think it's 10 to the minus 8. Part C asks for the charge induced, okay, something a little different here, on the face of the dielectric after it's inserted. The charge induced. We derived an equation for that. So Q induced is equal to Q naught times 1 minus 1 over K. And we have all of those values. I'm still going to go this direction. I'm just going to climb over you. You don't care, right? That's fine. It'll be fine, because I wanted to go up here. Chronic tacos. I remember the chronic tacos from before. So if you plug those numbers in, let's see. I've got a value for that. It is 1.19 times 10 to the minus 8. Notice the charge induced on the dielectric is less than the charge on the plates, as expected. Part D, ask us to find the electric field in the space between each plate and the dielectric. So if we were to go over here, zooming in, zooming way in, it's asking us to find essentially this electric field, which is E naught, and it's going to be the same as the electric field that's over here. It's the electric field that's being created by the charge on the plates. So keep in mind, the charge on the plates doesn't change when I insert the dielectric. That electric field is still there, and it's still being created. So maybe we should make a little note here saying that Q naught hasn't changed. And it is creating E naught. So let's see. We could say that E naught is Q over epsilon naught A. Well, that's going to be Q naught. And we have all of those numbers, so that's 7.5 times 10 to the 4th volts per meter. The charge on the plates is still the same, so it's still creating the exact same electric field in that space where there is no dielectric. Notice that part E asks us to find the electric field in the dielectric itself. So that's not the induced electric field, that's after we take the two electric fields and combine them. So that is E naught minus E induced. It's asking us to find E sub D, the electric field in the dielectric, which we already know is going to be E naught divided by K, the dielectric constant. And it's part F that I've been really wanting to get to. So this is going to be 2.14 times 10 to the 4th volts per meter. And then part F asks for the potential difference between the plates after the dielectric is added. The potential difference between the plates after the dielectric is added. So we could use the relationship between the electric field and the distance between the plates to help us find that potential difference, but it looks a little different than what we've done before. So we could say that V is equal to minus the integral of E dot dl from one plate to the other one. And let's say it's from the right plate to the left. So let's write this as from negative to positive. That means my dl vector is going to be pointing to the left, but all of the electric fields are pointing, well, at least one of the electric fields is pointing to the right, which means I'm going to end up canceling out that negative sign. So we need to break this into two parts. We could say that this is E times D minus L. So D minus L just gives me the space or the path where there is no dielectric. D is the full spacing, L is the width of the dielectric. And let's see, we can add to that the electric field in the dielectric times the distance over which that electric field is occurring. So L, again, is the width of the dielectric. If you put all of that together with the numbers we have, you should get 96.4 volts between the two plates. So you can still use the same relationship we had before with electric field and potential difference. Just be careful that you're using the right electric field for the spaces that you're considering. And here we have two different electric fields that we have to worry about. And then finally, G. G says, what's the capacitance after the dielectric's in place? There's a number of different ways we could go about this. Let's just say C is Q over V because we have those pretty easily. And that's going to give me 172 picofarads. And at that point, we are done with chapter 24. Does anybody have any questions? Just applause, right? You want to do applaud? We will applaud. Fantastic, it is done. But after the applause, there can't be questions. I'm sorry. No. Okay, fine. Starting here. At the that's E sub D times L. So the electric field in the dielectric times the width of the dielectric. Yes. In that particular case, that is, it's going to be Q naught because it's not connected to any battery. Q naught and Q are the same, but it wouldn't be Q induced. And down front, yeah. Why are we subtracting D and L? That's to give me just the white space. So we're taking D, which is the distance from here to here, and subtracting L, which is just that distance, which is going to give me this plus this. Okay. Anybody else? Anything you want to say about capacitors, or you want just capacitors to die? Let them die? Wow, that's mean.